and welcome, or welcome back to the third episode of Whether or Not. This time we have something a little different for you. I think you're going to like this, so please stick around. I am Stella Q, and I have a confession to make. I'm addicted to sky gazing, and I'm happy that you're here because I'm guessing you're probably also hooked on sitting back and observing a juicy thunderstorm roll in. There's nothing better. And I also suspect that we may share similar concerns about what exactly is taking place up there sometimes in the wild blue yonder right above our noses. Is it weather or not? TM question mark. Well, as fate would have it, I know a guy. His name's Jeff, and he's had his head in the clouds for many moons, but his feet are also firmly on the ground. And he happens to know a thing or two about reading the signs by studying intricate data and funky coloured maps and graphy things with lots of very important squiggly lines that mean stuff. And he speaks the language. He's ready and very willing to translate to the rest of us with pictures, and he brings receipts. Our investigations are after the fact, backcasting if you will, a genre we have introduced as meteorological forensics, which entails hours in the study of many different unique aspects, both atmospheric and terrestrial, and piecing together bits of the puzzle of a weather event in an attempt to separate fact from fiction. And with no affiliations with anyone or anything but the plain truth, we have no chains. We just want to know. Same as you. Speaking of facts, here's some good news. We can learn to do this too. Fair dinkum, we can. Granted, Jeff has a lot of experience from his time spent as a meteorologist in the Navy, but his love for the profession has never waned. Only the technology has changed and it's improved exponentially, adding ease and accuracy to the equation. And Jeff loves to assist others to view our skies with wiser eyes and in their truest light. But you can't read a book if you don't know the alphabet, right? So, let's wise up and take off to sky school together, starting at the very bottom of the sky with clouds. Come on, let's get skywise. Hey Jeff, how you going?
Hey, doing really good, Stella. How are you?
Very good. I've had my head in the clouds and I've been anticipating this for quite some time, so please, fill us in on the anatomy of clouds.
What we're going to cover today, cloud identification and more. You're going to see a whole bunch of pictures of clouds. There are 27 main types. And this is going to be kind of a two-part video. Part one is going to be mostly the pictures of clouds, a little bit about each. You're going to be introduced to the International Cloud Atlas, which is the Bible of the cloud folks. And part two is going to be what causes clouds, some of the physics. Why do they look like they do? Why are they puffy or flat? And how do they form? And we'll get into some of the unusual clouds as well. A little bit on both parts.
Sounds excellent.
Okay, so let's talk about the Earth's atmosphere first of all. So there are 4 layers. Right here it shows it in 5, but there's actually 5, but we can break 2 of them into one. I'll go over that as we go upward. So first of all, near the Earth's surface, you have the troposphere. Above the troposphere is the stratosphere, then you have the mesosphere, and then the thermosphere and exosphere those together are frequently called the ionosphere. So some of the features of each of these is troposphere goes up to about 7 miles, the stratosphere goes up to about 31 miles, the mesosphere up to about 50. These are not static numbers, they're approximate. Mm-hmm. Thermosphere goes up to 440 and 6,200 miles is the top of the exosphere approximately. So what you see in each of these is all the weather happens down in the troposphere. You have a lot of jets flying in the stratosphere. Not a lot. There are actually few. It's the CEOs that fly up there. Up at about 45,000 feet is their assigned level. That's where your Learjets go. And Stella once referred to it as the elitosphere.
TM.
TM. In the mesosphere, you have that's where the meteors burn up. Once you get up into the thermosphere, there's a radiation belt up there. There's also the auroras, space shuttle, and the ISS. Above that, you have the majority of your satellites. And way above this, about 25,000 miles up, is where you have the weather satellites that take the full disk pictures of the whole globe.
Mm-hmm.
Next slide. This gives you some of the features on temperature, pressure, density, and speed of sound. So you can see the speed of sound is the blue line, the temperature is the red line, the density is that brown line, and the pressure is that green line. So in the troposphere, up to the tropopause, you have decreasing speed of sound, decreasing temperature, decreasing density, and decreasing pressure the higher you go. Once you get to the stratosphere, the temperature and the speed of sound both increase up to the stratopause. Density continues to decrease on all four of these. In the mesosphere, you again have decreasing temperature and decreasing speed of sound. They parallel each other, the temperature and the speed of sound. And in the thermosphere, again, they start to increase on the temperature, increase in speed of sound. The mesosphere is the coldest part of the atmosphere. Top of the mesosphere, at the mesopause, you have your minimum temperatures. Any questions about this, Stella?
No, you're explaining it extremely well. Thank you.
Okay, so let's move on. So there's a good little website called What's This Cloud? It's great for novice cloud watchers. It shows, here's a nice picture that shows the types of clouds there are, and we call these etages. So the low etage, the mid etage, and the high etage. In the low cloud group, you have your cumulus, your stratus. SC is stratocumulus. In the mid etage, you have altocumulus, altostratus, nimbostratus, but the nimbostratus extends down into the low etage. Then you have your high etage, which has cirrus, cirrocumulus, and cirrostratus. And you have this big guy over here, thunderheads, with the anvil top. That extends through all three. They start down low and they build, and they actually hit the troposphere and flatten out. This has all the abbreviations. It has the summary about them, a little bit about them, like, for instance, cumulonimbus thunderstorms. It has their altitude range, approximate. So typically your low clouds are below 6,500, 7,000 feet. Your mid clouds are between that level and about 20,000, 18, 20, 23,000. It's variable, and the cirrus go up above that, up to 49, 50,000 feet, and they top out at the top of the troposphere at the tropopause.
All right. The Thunderheads is definitely going to be the name of my next heavy metal band.
Okay. Powerful name.
Yes.
Okay, so this is a good Cloud Identification 101 website, but the go-to source is the International Cloud Atlas. This is the Bible. The 2017 update was specifically made for online. And that last update was prior to that, 1986. So when you go here, there's a beautiful little explanation of a video, a short video, 2 minutes, 39 seconds, that will actually tell you what's new about this. And then you have a couple other little videos that talk about it as well. But this is the atlas that we're going to use for talking about all the clouds today.
Excellent. And we will have that link down in the show notes.
Correcto. So principles of clouds classification. So clouds continuously evolve and appear in an infinite variety of forms, but there are a limited number of characteristics that are used to group them. So like people and all animals, the scheme that is used is has Latin names of genera, species, and varieties. So like humans are Homo sapiens. Homo is the genera, sapiens is the species. Some clouds get into the variety as well, so you'll have 3 names.
I didn't realize that.
We're going to talk about special clouds and upper atmospheric clouds as well. Let's get into
clouds.
Special clouds. So, coding of clouds. Weather observers follow a set of rules. And if you were to go into this cloud atlas, this has a frame by frame. You just hit the next button, go on to the next, and they walk you through everything you want to ever know about clouds. So this atlas is very comprehensive. There are special rules for each of these, and they're abbreviated. Subscript L?
Subscript, yes.
Clouds low, clouds medium, and clouds high.
Right, so CL, CM, and CH. Okay.
Correct. Yep.
The coding of clouds.
Coding. So now we're going to get into each of these and what they look like. So starting at the bottom, low cloud type 1, your typical summertime cloud that you see when it starts warming up every day. That's seen in large parts of this country anyway. That is your initial formation of the clouds. They're just little cotton balls. Mm-hmm. So they have a name: cumulus humulus, or cumulus fractus of dry weather.
When they grow up, they want to be thunderheads.
Yes. That is your low cloud type 1. Type 2 is cumulus mediocris or congestus. So back when I was doing weather back in the Navy days, we called them moderate cumulus or towering cumulus. So you could just see that they grow up from tiny little babies like way back there, and they get bigger.
The beautiful ones that you want to bounce on. Yep. Artists' favorites.
Yes, the pretty ones. So moderate or strong vertical extent. They have towers and domes. Strong vertical extent, generally with protuberances in the form of domes or towers. Okay, let's move on to the next one. Low cloud type 3, cumulus cavus. Intermediate stage with tops lacking sharp outlines. So they can also be there with cumulus or stratocumulus or stratus, but this gets the top priority. There is a ranking system on how the observers have to report clouds. So we'll see that eventually here. Mm-hmm. This happens in the later parts of the day, usually when they get this big, maximum heating parts of the day, not so much at night.
Right, okay.
Okay, so type 4.
Because it's all very symbiotic, isn't it? I mean, obviously, clouds are forming because of things like terrain, temperature, etc. So, yeah.
Correcto.
Yep.
Type 4, stratocumulus, cumulogenitus. They result from the spreading out of cumulus when a top reaches a stable layer. So you could see there are cumulus clouds right here, down low, and there is a stable layer, which means there's a warm layer of air that came in above that. And what that does is it causes this to flatten out because the air can't rise through it, even though you have a heating source or a hill or something that's causing the lift. But because that warm layer is up there, they hit it, they can't rise farther, so they flatten out.
Okay.
Type 5, stratocumulus non-cumulogenitus. So this is the stratocumulus. You still have the flat layer, but you don't have cumulus below it. It's still telling you the same thing, that that atmosphere is stable, that you won't get strong vertical growth, which means you won't get strong showers of any kind.
They tend to loom and just hang around a lot, don't they?
Yeah. They just decrease the temperature. So block some sun. Okay. Type 6, stratus nebulosus or fractus, of dry weather, or you can have both. So there's your stratus picture. Think of San Francisco in the summertime. What is that? How's that saying go? Coldest winter I ever had was the summer in San Francisco. So these are transitory stage during formation or dissipation of stratus layer. Single sheet, fairly uniform base. They can almost come down to the ground, and once they do touch the ground, you call it fog.
Right, okay, that's the difference. So once it touches the ground, it becomes fog. Got it.
Correcto. Type 7, stratus fractus or cumulus fractus. This is associated with wet weather. So when you have the clouds that were higher were precipitating, raining on the ground, and then you have maybe warm ground from when the sun was out prior to that, that water evaporates, and that causes these little guys down below, which are just like baby clouds that are due to that evaporation. Okay. Low cloud type 8. This is when you have bases at different levels with cumulus and stratocumulus with bases at different levels. Cumulus may penetrate the stratocumulus, but it does not spread out and form the stratocumulus. That's the difference. So they are just unique levels where the cumulus does not spread out into the stratocumulus.
We get a lot of comments about if we could just go back for a sec, the stripy sort of look. What causes that? Like the one on the bottom right.
There's some instability there. Yeah, they're kind of puffy, but they also flatten out. So anytime you have stratocumulus, that there's a stable layer above. When you lift air, it cools. When it cools, it causes a cloud. When you make the air descend, it warms, and that causes the cloud to dissipate. So you have uplift and you have downlift happening here. Everywhere there's a gap, that's where you got downward moving air. Everywhere there's a cloud, you have upward moving air. So it's kind of like the air is going up and down underneath that inversion, and the inversion is causing them to flatten out. They're forming and dissipating right next to each other. So you have up and down motion of air up there.
Oh, okay. All right.
Okay, low cloud type 9. This is the big daddy, cumulonimbus capillatus. Often they have an amyl top. None of these right here show that. But this picture over here that depicts it, artist's drawing, shows that amyl top. Right. So these are the guys you don't fly into. They'll go up to the tropopause and spread out. You go around them.
Right, okay.
As a pilot.
So obviously each plane has to have a little bit of extra fuel to allow for these possibilities?
I'm sure, when you're at the airport, when you know your destination, they have to they know from air traffic control already that they're going to be going around what there is. Like when you had the Dallas situation, not Dallas, Houston a while back, I was watching the flight radar, and there was just this humongous, probably 100-mile wide area where everybody was just going around. So that's planned. Whoever's putting the fuel in the plane, they already know the flight path, and it's a calculated amount that they put in the plane.
Very specific. Yes. Wow.
Because they don't want to have a full plane because they're carrying extra weight. So there's a cushion.
Yeah.
And in an emergency, they have a extra amount to go off route in case they need to.
Yep.
Okay, so there are actually coding instructions for observers, and this is the coding instructions for low clouds. We're not going to go into them in detail, but there is a hierarchy. That's the point here, is to show that there is a hierarchy. The 9 is the worst case scenario, which tells you there are thunderstorms. A 3 is cumulonimbus as well, and that tells you there are probably thunderstorms in that area. Stratocumulus, formed by the spreading out of cumulus, tells you there's instability down below, but it becomes more stable. So anytime you see a low cloud type 4, it's, you know what to expect. You're going to get some turbulence on the way down, but it's not going to be terrible. And each of these just works its way down, and this is the hierarchy that the observers use to code the clouds.
So I suppose pilots and everybody involved would become so familiar with this, it would be like reeling off an alphabet eventually. It's just
pretty much.
Right. Okay. Very specific.
Most people aren't going to be using the secondary name, though, the species. It's just, you got stratocumulus, you got cumulonimbus, you got nimbostratus, altostratus. Most people are not going to remember that second name. But for the observers, that matters. So into the mid clouds. The difference, the thing here about this is you can see the moon or the sun through it. So it's more gray. It's got the gray color, but you can see in this picture, you can actually see the outline of the sun or moon.
Sort of translucent.
It's translucent. It does not give you a halo.
Right.
Mid cloud type 2 is altostratus opacus or nimbostratus. So it's thicker. You will not see the outline of the sun in a mid 2. This is the type of cloud that gives you heavy, steady rain, continuous rain, not showery, but continuous rain.
Good soaking garden rain.
Yes, the one that happens for 5-10 hours plus, that gives you just massive amounts of rain out of this. This is what you see with warm fronts. Mid 3, altocumulus translucidus at a single level.
We've been having a lot of this during our autumn, or what you call fall, here in Australia. It's been very beautiful to look at.
They are. I saw some pretty good altocumulus the other day here. We had thunderstorms here. A weak little thing, enough for a rumble, but you don't normally get that in California.
Right.
Some subtropical moisture came up and gave us about a day or two of this, and we had all these beautiful clouds, altocumulus included. Mid-cloud type 4, altocumulus translucidus. So this is your lenticular clouds. Very, very turbulent around those things. Usually it's over mountain or hills. It's telling you that you have some pretty good winds, and they change shape constantly. They're just beautiful, and they look like flying saucers.
They do. Yep, we're being invaded.
Yeah,
it's just a cloud, dude. Relax.
Enjoy the beauty. Okay, cloud type 5, mid-cloud 5, altocumulus translucidus or opacus. The difference here is they're in bands, and introduce a new word. Progressively invading means they're starting at the horizon, and as they're coming across, they're going all the way to the horizon and continuing to come at you. So the percentage of the sky covered by them is larger and larger with time.
Mm-hmm. Sort of a slow creep.
Kinda.
Okay.
Don't call me that. That's not very nice to you. Mid-cloud type 6. Alticumulus cumulogenitus or cumulonimbogenitus. This results from the spreading out of cumulus, like we saw earlier with the low clouds, but they spread out at a higher level, above 6,000 or 7,000 feet, which is the top of your low cloud etage. So then when you have that you have a stable layer up there. They can't push through it because of that stable layer. That's a good sign for pilots.
Mm-hmm. Not much turbulence.
Turbulence goes away. Here's some interesting stuff. Mid 8. This is what I saw a couple days ago. Alticumulus castellanus or flockus. You got these look like horses on the top on this left picture. So that's telling you got good instability up there. You're going to get a bumpy ride as you're flying through those clouds from pilot lingo. You see those? You see Alticumulus castellanus in the remarks, and you know that you're going to tell your passengers, buckle up. Sometimes these are accompanied by fibrous trails called virga. And virga is another name for rain that's evaporating before it hits the ground. And these guys right here on the right picture look like they have virga.
Beautiful.
Vertical or inclined trails of rain. I forget the actual acronym for the G and the A. Mid-cloud type 9, alticumulus of a chaotic sky. So when you have a lot of rain and stuff like that, you've got a lot going on up there. And when you have a hard time picking levels as the observer, you have to make an estimate on the height. This is the catch-all for when you have at several different layers. Mid-cloud type 9 alticumulus.
Looks complicated. So it'd be hard to pick. How do you pick which ones to tell a pilot about in a chaotic sky like that?
You follow rules like this. So coding instructions. So if alticumulus of a chaotic sky is present, the coding is 9. If you see a code 9, then you know that you got weather in that spot.
Right.
And in this case, if you look at these 9, 8, 7, 6, 5, 4, 3, almost a reverse order right here as far as importance of coding for the observers.
We've got 2 CM7s there. Why is that?
Good question. Let's see. If number 7.
Oh, 3 actually. There's 3.
3 7s. So very specific rules. If alticumulus is coexisting with altistratus or nimbostratus, it's 7. If alticumulus at 2 or more different levels, the coding is 7.
Oh, okay. I see.
And again, if it's a single level, it's primarily opacus, the coding is 7.
Right. So similar sort of situation, just slightly different presentation.
Yes. Yep.
Okay,
we're in the high clouds. Cirrus fibrous or incinus, not progressively invading the sky. So that means it's moving across the sky. It's not reaching the horizon. It's not increasing in content percentage-wise. It's just a patch moving through. Type 2, not increasing in coverage also. This is spiciatus, or that's supposed to be castellanus. That's a misspell. Or flockus. So you have 3 different types here. Patches or entangled sheaves that do not increase sometimes appear to be the remains of, that's what it was, the upper part of a cumulonimbus.
So you could fly through that, no worries.
Yes, there is no cumulonimbus attached. Okay, so this one is you have to have proof that it originated from a cumulonimbus. So right here you can see cumulonimbus in the background. There's a patch of cirrostratus hitting the troposphere, and this guy to the right is detached. So the upper winds are probably from that back direction towards us, towards the right.
Okay.
And that patch is proof. That's the proof that that came from a cumulonimbus.
Right.
High cloud type 3. Type 4, cirrus uncinus or fibrous, progressively invading the sky. So they're beautiful little mare's tails, as I think they call them also. And they're increasing in number as they come across the sky. Type 5, cirrostratus with or without cirrus, progressively invading, but less than 45 degrees above the horizon. So these
very specific.
This whole next bunch is all about the cirrostratus and what percentage of the sky they cover. So type 6 is greater than 45 degrees above the horizon. Same thing. Type 7 is covering the whole sky. And that's where you get the halo when you look through the sun, and the prism effect, because they're ice crystals and they're prisms.
Oh, okay. So the colours come from the ice crystals.
Correct.
Think Pink Floyd's Dark Side of the Moon.
Yes.
Cover, I guess.
Covering the whole sky, light, uniform, and nebulous veil showing no distinct details, or more or less clear-cut striations as fibratus. Type 8, not progressively invading and not covering the whole sky, is the only distinction to that. And then type 9 is cirrocumulus. And that's telling you have some turbulence up there, that you have some overturning of air.
Yeah. Okay, that's what's creating those little ripples.
Correct.
It's not HARP, Ben?
It's not HARP.
Okay.
It's telling you have some cold over warm situation, and cold over warm, think of it like this: warm wants to rise, the cold is denser, wants to sink. So you have turbulence up there.
Mm-hmm. Okay.
That's what
sort of
causes
fighting
that.
with itself.
Correct. Okay, so there's your rules for the high cloud coding instructions for the observers, and it's almost a reverse order as well. The 9 is the most important in all three of the cases, low, mid, and high, and the 1 is the least important as far as telling pilots what's happening up there, or other weather observers or forecasters that are doing the brief for that pilot.
So how would you present this information to a pilot? Would it be just like a verbal, it's CH9, CH, like how would it come out for them to see it?
The only thing they really worry about is, am I going to have turbulence? Am I going to have icing? Am I going to have bad weather on landing? So
right.
You don't tell them the type of cloud that you're going to have. It's like
just code.
It's the code, but the code is for the forecaster to know what's there when he's assessing what's there as he's making the brief up.
Okay, so does he get like a piece of paper that's read out, or how does he receive that information?
Well, I'm sure everything's by computers today. So just like this, I have access to so much that I didn't have before. We had teletype years ago. The satellite things came out one every 20 minutes on paper. They burnt onto the paper, and then you hang them on the wall. Kind of dates me age-wise, but
yeah. I asked.
So everything at your fingertips, at your request right now. Very quick information, just like everything else on the internet.
Yep.
So there are classification aids within this International Cloud Atlas that shows you flow diagrams to make the decision of what type of clouds you have. And I have a blow up of one of those. They have one for all three levels. the next one shows how you determine your low clouds. Is lightning or thunder heard? Yes or no? And then you go down and ask the second question. And if it's yes, you go there. And if it's no, you go there. And I don't show the whole thing here, but it helps you come up with the actual cloud that you have name-wise.
Oh, okay. Like a flow
That's pretty
chart.
cool.
Nice.
Flow charts. Yeah, that's wonderful.
And you can
Okay.
download that by the looks of it.
Yeah, and you can download it as well. Correct. Now the fun clouds, the ones that are not often seen or seen often and pointed out by sky watchers. So I've never seen a nacreous cloud. These are stratospheric clouds. Absolutely beautiful. Polar regions in the stratosphere.
Yes, these are very, very, very long way away, very high up. Yeah.
Yeah, so, these are probably 60, 70, 80,000 feet up. The stratosphere in the wintertime, well, if it's in polar regions, your stratosphere starts at about 25,000 feet, 20,000 in the winter, and probably gets up to 30,000 in the winter or in the summer. So above that.
Right.
Noctilucent. These are polar mesospheric clouds. So we're talking up to 40 or 50 miles up. So you would see that a long ways away. Upper mesosphere, coldest part of the entire atmosphere. Silvagenitus. This is a forest is silviculture, I believe is what it's called. So when you have a rain and that cloud layer saturated those trees and the sun comes out, that starts to evaporate from those trees and you get the little wisps forming over the tree line versus out in the field, it's not doing the same thing because the trees gathered more water than that grass did.
And it rises as the sun is rising and warming everything. The moisture level is going
Stratus silvagenitus.
Beautiful.
Flammagenitus. This is above a forest fire. That extra heat, and if there's a moisture source, that's what you're going to get.
That's not just smoke. That's actually a cloud.
Yeah. Yep. You would think in the summertime it's not going to be as pronounced because, at least in the west of the United States, you have a lot less moisture in the trees the farther you go into the summer. So I'm sure that has something to do with it, how prominent that's going to be. Homogenitus. This is over industrial plants.
Boo.
Yeah, so, the product of combustion, one of the things is water vapor. Every flame from every type of combustion gives you water vapor as a byproduct, along with the CO2 and other things.
So that is like actually creating weather in one sense. So this is the man-made sort of stuff. But they wouldn't be able to have these very close to airports, I would imagine.
I would think not on the upwind side, which means usually western half versus eastern half, because the winds typically go from west to east. Could be southwest, northwest, west. That's the direction wind is from. So I would not anticipate having one of these anywhere on that western side of any airport.
Of course, that would depend where you are in the world.
Correct. That's northern hemisphere, not southern hemisphere.
Don't forget about us.
Nope. Okay, so here you have your lenticulars, and this is something called orographic influence. If airflow is crossing a hill, mountain, or ridge, orographic clouds may occur below, at, or above the tops of the obstacle. They show a lenticular right here, and you might also get something called a mountain wave on the leeward side, which is the downwind side. And we'll be covering those in detail and probably doing a special class on that because there's a lot of discussion about mountain wave clouds as far as being HARP.
That's the lee waves, is it?
The
Are you
lee
talking about?
waves, gravity waves, mountain waves, yes,
They
but
have
they're
a
not
few
shown right
names.
here.
No. Yes, we
Uh,
definitely need to. We will go into that in more detail another time.
there's your lee clouds right there. So you get
There's the troublemakers.
so there's some islands that are protruding through the clouds. It's a stratus layer, and the wind you can tell is coming from here. And it looks like there's alligators or something coming up to the southwest. But
Oh, yeah.
what that is there's a stable layer of air, and it's causing the wind is flowing up the southwest side of the islands and going up, hitting the inversion and going back down, coming back up, going back down. Every time you have it going back up, you're creating a line of clouds. And as it descends, it starts to dissipate because it's heating as it descends. So,
Yes, I think one of the most useful things that I've heard recently about the clouds, etc., was when Jim Lee, shout out to Jim from climateviewer.com, he said just, I can't remember the exact words, but he said just sort of think of the sky as sort of like a river or a fluid flow of moisture, and it just really made me click. It's like, oh yeah, of course, you know. So yeah, looking down at there, as you said, it could look like a bunch of alligators swimming through, but if we need to sort of think of it that way.
that is fluid, yes.
Yeah.
Here we go, over Tasmania. I've seen them over Ireland. I've seen them over the Western United States. I'm seeing them. I mean, there's hardly a day that goes by that I can't find lee clouds somewhere. They were really prominent yesterday in the West. And you need strong winds, you need an inversion, and you need moisture.
Is there any way that can be produced from, a man-made equipment sort of source
Wow. The
that you know of?
fear mongers on several YouTube channels seem to say it's HARP or NexRad, but Jim Lee did a lot of stuff on that recently on his videos at climateviewer.com, and
Yes, he did.
they were saying this is NexRad or this is HARP, and he debunked that very well.
He did. And I happen to know that, just see there on the very sort of the bottom right, there's a little island. That's just off a place called Eagle Hawk Neck. I used to live in
There?
Tasmania. Yeah, that's it, pretty much there.
Uh-huh.
Just right in the south of that somewhere, there's a little island, which actually does have a HARP station, I suppose. I'm not sure if it's still active. I think I really don't know, actually. I shouldn't say I think it is, because I don't know, but I know it's there. But even if that was operating, it's in exactly the wrong place for that particular situation that we're looking at there. That's the opposite of what it would do. If that was HARP, it would be the other way around, those lee waves.
Well, HARP is a ionospheric heater and aimed straight up, right, at the ionosphere. They're not aimed to the west. It's aimed straight up because you're trying to get 50, 100 miles up with that energy to do what they do.
Yeah, they're not really there to play with clouds.
Correct.
It's not really much point.
Here you have a satellite view that shows the lee clouds over Nevada primarily. I've seen it to where 4 states have been covered with lee clouds when you have really strong winds out of the west. Here we go into the geoengineering talk. This is the one thing that gets the most talk over anything. So, Cirrus homogenitus, created by man. Homogenitus, man created these. So here we have a good checkerboard pattern, checkerboard tic-tac-toe pattern. Lots of talk about these things. Do they persist or do they not? So you have 3 main contrail types. They have right here short-lived, which they also called ephemeral, persistent non-spreading in the middle, and persistent spreading. And these guys will eventually form just a thick layer of clouds, which top out at the troposphere, flatten out, and cover the sky.
We've all seen that
On so many occasions. So here's a good example of where they're spreading out. This was 12, 24, 23. Virginia, I mean, multiple states covered. Southern Illinois, not quite up into Indiana, Kentucky, Tennessee, down into Alabama, Mississippi, Georgia, large area.
Okay, so why are we seeing that in... Oh, not so fast, buddy. Back up.
Okay, all righty.
Why are we seeing these contrails in this sort of little area? Can you just explain the conditions that would make that happen as opposed to not seeing them up there in North Indiana?
There's actually a name to those zones. It's called ISSR. That's ice supersaturated region. So you have upper level moisture coming from some water source getting into the upper atmosphere. And we're going to be talking about all those methods of getting it up there in the second part. But
okay. Right.
That moist area is floating over this area. And as aircraft fly up and out through that, up and down and in it, they add moisture. That addition of moisture from the combustion of their fuel, their kerosene that they burn, adds moisture to that already wet area. And it produces the jet exhaust trail every time because of that.
Yeah, so it's basically sort of unintentional cloud seeding. Would that be correct?
Yes. The seeds are your soot particles from the pollution that's in the jet fuel.
Yes, right, okay. And can we also just go back a couple of slides back to that cross grid? Because I'd like to talk about that for a moment. Okay, so it does look like an intentional thing. I mean, you can understand people saying that. I exactly have said that same thing myself. So can we talk about why it is that it becomes a grid, please?
Okay. I'm going to go forward one or two slides. Okay. I'm going to skip.
Sorry, I didn't mean to upset your flow there.
I have an actual website to go to.
Maybe all right. We'll keep just going. And if you're going to address that, then we'll...
Okay. I think towards the end of the video, it might be a good way to close out because I'll finish up with the slides first and then jump to that website and change the screen over to that. So assessing the sky, is it a contrail? So there's a jet trail in the sky. You need to look at several pieces of things. First, your eyes are going to see it. Then you go to the satellite, and I cover... I'll put links in there that show the satellite views to use. And Radiosonde data will tell the levels of the moist area, the ISSR, and whether or not you should see a contrail. And then you have your flight radar apps like Flight Radar 24, or ADS-B, FlightAware, SkyGlass. You need to determine, is that a contrail? You need to use these four things, at least three of them.
Yeah, you can get by without the Radiosonde, can't you?
That's, to me, more important than eyes or satellite.
But most sort of, mums and dads probably don't know how to read a Radiosonde, but you can actually determine quite a lot with just the app, can't you? Just knowing the location, the time, and have one of those apps so that you know the plane. Would that be right?
The app? What are you referring to, the app?
Well, like Flight Radar 24, etc.
It's kind of a comprehensive thing. You need, at least in my opinion, if you don't have Flight Radar, that's the thing that helps you prove it because you know the altitude of that aircraft.
Yep, that's what I mean. Okay.
So I think I have a few slides that show something along this. So here's a Radiosonde numerical data on the left, and on the right, this is Dallas-Fort Worth. That red line is the temperature line, and that green line is the moisture line. And we're up towards the very top. This 300 right here is 300 millibars. That's about 30,000 feet. And 200 millibars is, in this case, 13 kilometers. That's about 40,000 feet. That's the stratum that aircraft fly in, their cruise altitude.
Commercial type flights you're talking about?
Correct. Yes.
Okay.
When these brown lines are 10 degrees apart, these sloping brown lines. So anytime you get less than 5 degrees, you have clouds starting to form. And you could see from, if that's 30,000, that's 40,000, this is about 33,000 feet. That's about a 5-degree spread. It widens out a little bit, and then it comes closer together. And right at the tropopause, it's 2 or 3 degrees apart. That whole 33,000 to 40,000 foot layer is, you could see the actual numbers over here. So it shows the temperature, the height, the dew point, the relative humidity, and the dew point depression. That dew point depression is the number we're talking about. That's the difference between the temperature and dew point. Anytime that's below 5, and you see a whole bunch of numbers in here, up near 200 millibars in this case, let's see, there's a 2.6 dew point depression right there, 11,000, 12,000, this is pushing 40,000 feet, where the humidity is really high. And when you add jet exhaust into that and add more moisture, you're leaving a contrail.
Okay.
So that's the Radiosonde data numerically and graphically. And here's for instance, right here, where over Dallas, again, this is the same depiction that shows what was happening that day because that moisture was up there. And here you have in California, and you could see this whole Central Valley down near Fresno. There's a lot of aircraft traffic up there, and I have filters set up for 35 to 40, 40 to 45, and 45 to 50,000 feet. All these aircraft are going through that area, producing those trails.
Okay.
How do you explain these patterns? There is a contrail simulator, and I think this... Okay, so here we have a contrail pattern simulator. This was done by Mick West over at metabunk.org. And what you see here is 2 aircraft intersecting. So you got one coming from the west going to the east, and one coming from the northeast heading to the southwest. So as that aircraft comes across, it leaves a contrail. As that aircraft comes across, it leaves a contrail. And based on the wind direction and speed that I have set right here, you have 3 inputs right here: plane speed, wind speed, and wind heading. So I can speed up the plane. I can change the wind speed to where it's faster, and I can change the direction of the wind if I want. And that's going to give you a apparent what it looks like when the wind pushes those contrails across the sky.
That's brilliant. Big shout out to Mick West for this one.
It's pretty awesome.
It is amazing. Okay, well, that really shows what's happening here. It's not, I'm not going to say 100% of the time because I don't know, but it looks like what is a nefarious kind of look of, the grid system, they're spraying us like bugs, is actually just the terrible fuel doing its thing, because let's face it, there's always fuel and particles in the sky. It's just the contrails make it visible. Would that be a fair assessment? Okay.
Yes,
so
exactly.
the contrails sort of happen because of certain conditions, flying at a certain height, at a certain temperature, etc. And then as the wind is, or the breeze, whatever, the wind is blowing as different planes are taking off along similar flight paths or the same flight path, therefore we get a checkerboard look. Yeah?
Exactly, because those are jet routes. Those are specific routes from airport to airport. They have to follow that jet highway at the exact specified altitude. And typically, if you have a northbound flight along that jet route, it's 1,000 feet different from the southbound flight. So they don't obviously get close to each other.
Yeah.
So
Okay.
every one of those aircraft right here, and like if I change the direction just a little bit to be more from the south, it would look like this.
Okay, so depending on the conditions will be whether they spread out or stay as thin streaks.
Yes. And like here you see the thicker one versus the thin one. That thicker one is like if the wind was parallel to that contrail, it's not going to spread out sideways. It's going to stay closer to itself longer and not move as much. That makes sense what I just said?
Yes, whereas the other ones then would spread out if the wind was from that direction.
Right. Here's something interesting too. This is kind of cool. So if you have an aircraft doing a landing pattern, for instance, when you come in from a different direction you have to land into the wind. So if you were coming from the east and you were landing into the west, you would just come straight in. But if you had to circle that airport to come around to land into the east, this is what happens, and you get a spiraling pattern.
Which does look very odd. You can't really blame people for going, what the? But it's just the nature of the thing. The nature of flying a plane and trying to land it, I guess.
Yep. And all that would require is just having to go around the airport to come back towards it.
And it's sometimes planes have to go around and round and round because they're waiting for something. They're waiting to be clearance, what have you. So it might go on for a bit.
If you have a hold on fog, the ceiling might be, under 100 feet or 200 feet. They have to wait for that to clear. So that kind of covers that. That's the first part.
So let's just sort of, as a summary, most people are looking at these skies and they're spraying us and, blaming the Bill Gateses of the world and those other reptilian creatures. But really, we should be looking more at the airline industry itself. I mean, nobody wants more regulation. Nobody wants more rules and etc. But in this circumstance, it's the fuel. It's the fuel. That's the problem.
It's the unrefined. I mean, it is refined, but kerosene is not as refined as gasoline. They don't remove all of the stuff that's in that oil, and that's depending on where that oil came from, what's in that ground, mineral-wise.
And were they burning biofuels or something now?
That too. I mean, Jim Lee talks about what they call it, SAF.
Yeah.
Sustainable aircraft fuel made out of oils and waste products from different things.
That would have to vary a lot, though, you would think. I mean, it couldn't be purely consistent.
What are their feedstocks? Go to Jim Lee's Climate Viewer, and he talks about that stuff in very much detail.
Well, we'll put a link in the show notes for that one.
That concludes part 1, unless you have any other questions, Stella.
Well, we're going to go into a few things in more detail in part 2, I believe. So I will just hold my questions in anticipation. If anybody is watching and they've got any questions, please don't hesitate to forward some. We'd love to address them. We'll probably do a question and answer show at some point because we do have a few people putting some questions forward. We will catch you again in part 2. Thanks for watching part 1, and we'll look into a little bit more detail coming up. Thank you for that, Jeff.
Thank you. Been fun.
All right. Talk to you soon.